Good day, everyone. In this video, I'm going to discuss divisibility and the division algorithm. So let's start first on the divisibility. So if A, B, and C are integers such that C is equal to A times B, then A and B are factors or divisors of C, or C is called a multiple of A and B, or C is divisible by A and B. So for example, if we have 14 is equal to 7 times 2, we call 7 and 2 are factors or divisors of 14. And then here, 14 is a multiple of 7 and 2. Or we say 14 is divisible by 7 and 2. So that's it. So for simplicity, we write this symbol to this. Now, if A and B are integers such that A is not 0, then we say A divides B. If there exists an integer k such that B is equal to k times A. So if A divides B, we say A is a factor of B, or B is a multiple of A. And we write this notation. Now, if A doesn't divide B, we write this. So for example, by the way, in our example here, we can say that 7 divides 14. Why? Because from the definition, if A divides B, where A here is 7 and B here is 14 in our example, there exists an integer k such that we can write down 14 equals k times 7. So we know that 14 is equal to 2 times 7. So our k therefore is equal to 2. The existence of k, an integer. We know that 2 is an integer here. So we can say that 7 divides 14. Or we can also say that 7, here's A is a factor of B. So we can say that 7 is a factor of 14. So here, or 14 is a multiple of 7. But we also have here 2 divides 14, right? So now in this case, our k is 7. So we know that 2 divides 14 because we can write 14 equals 2 times 7. And this time k is 7 if we have this. And then another one, 14 does not divide 7. Why? Because we cannot write 7 equals an integer times 14. So we cannot find an integer such that if we are going to multiply it to 14, the answer is 7. Okay? So 14 does not divide 7. So we have that one. So let's have here an example. We have here 4 divides 12. Since we can write 12 as the product of 4 and 3. or 12 has factors 4 and 3. Or 12 is a multiple of 4 and 3. So here, -5 divides 50. Since 50 can be written as the product of -5 and -10. Here, k is equal to -10. The existence of an integer k, which is equal to -10 in this case. Then the third one is 2 divides 0. Why? Since we can write 0 equals the product of 2 and 0. Then here, number 4, 10 does not divide 5. Since 5 is equal to 10 times 1/2, here k is equal to 1/2. We can only get 5 if we multiply 10 by 1/2. Take note of that. And k here, which is equal to 1/2, is not an integer. Now notice in our definition here, k should be an integer. So 10 does not divide 5. So let's have here remark 1.4. Note that any even integer has the form 2k. So for any integer k, just like 2 times 1 is 2. Next even number is 4. It could be written as 2 times 2, where k is 2. Next is, say for example, another is 8. 8 is an even integer, so we can write 8 as 2 times 4. So 4 then is equal to k. Well, any odd integer has the form 2k plus 1. So any odd integer. So for example, we have 7. We know that 7 is an odd number. So we can write 7 as 2 times 3 plus 1. So here, k is equal to 3. So take note that any odd integer can be written as this form, as in this form, 2k plus 1. So here, the existence of k is 3. Thus, in this case, since for even, we can write this as, we can represent any even number as 2k for some integer k. Hence, in this case, we can say that 2 divides n. So for any even integer n. So see, n nato here is even. Because we can write n as this one, 2 times any integer. So when we say 2 divides n, from the definition, we can write n equals 2 times any integer, so for even. That's why for any even integer, we can have 2 divides n, where n is even. And then for odd integer, we can say here, 2 does not divide n, where n here is odd. So because we cannot write that as this form. Okay, next, for all integer a, for any integer a, we can say that a divides 0. Now, as you noticed, any number, any integer a, say for example, we have 5. 5 divides 0. Why? Because we can write 0 be equal to 5 times 0. So, for example, if we have 11, 11 divides 0. Why? Because 0 is equal to 11 times 0. So any integer divides 0. And next, if an integer b, b is an integer such that the absolute value of b is less than a, and B is not 0, then A does not divide B. So let's consider here an example. Say B is equal to 4 and A equals 10. So we know that the absolute value of B, so of course the absolute value of B is 4, which is less than A, which is 10. And we know that B is not equal to 0. Then we can say that 10 does not divide 4. Is it clear? 10 does not divide 4 because we cannot find the factors of 4 with 10 and any integer. So we cannot find any integer such that 4 is equal to 10 times k. So we cannot find an integer here. So 10 does not divide 4. So let's have here another example. We have 2 divides 26. Why? 2 divides 26 because in the first remark, 26 is even. So 2 divides 26 because we can write 26 equals 2 times 13 here. Then number 2, 105 divides 0. So this is for number 2 example. So we can write, because we can write 0 equals 105 times 0. Then here, 10 is less than 20. So B here is 10, A is 20. And we know that 20 does not divide 10. Again, because we cannot write 10 as the product of 20 and any integer. Here, we let B here be a negative number. So B is negative 6 here. And we all know that the absolute value of negative 6, we have here the absolute value of negative 6 is 6. And it is less than 30. So 30 here is A. Hence, 30 does not divide negative 6. Okay, let's have here theorem 1.6. So for this theorem, A, B, and C are integers, such that A divides B and B divides C. Then A divides C. Now, as you notice in this theorem, we have here A divides B and B divides C. Then we can say that A divides C. It is transitive property. So let's have here an example. Okay, for example, we'll let A be equal to 2, B equals 4, and C equals 12. So we know that 2 divides 4. So A divides B. Why? Because we can write 4 as 2 times 2, where our K here is 2. And we also know that 4 divides 12, for B divides C here. Why? Because 12 can be written as 4 times 3. So our K is 3. This implies that A divides 12. It means 2 divides 12. Yes, of course, because we can write 12 equals 2 times 6. So in this case, K is 6. Okay? So let's prove this theorem. Okay, take note. We have here our assumption that A, B, and C are integers such that A divides B and B divides C. Now we're going to show that A divides C. So we have here, by assumption, we have this one. Then, by definition, A divides B means existence of an integer. So we have here A divides B and B divides C. By definition, there exist integers K1 and K2 such that we have this. For A divides B, we can write B is equal to K1A. So existence of an integer K1. And for B divides C, we can write C is equal to K2 times B. As a result, we substitute. So since B, take note again, if A divides B, we can write this as B equals K1 times A. Now, if B divides C, by definition, we can write C equals K2 B. And then if we are going to substitute from here, C is equal to, substitute lang si B here. So we have here K2, C is equal to K2, then B here is K1A, or we can rewrite this one as K1, K2, A. So commutativity, we applied commutativity here. So that's why we have this C equals K1, K2, A. And hence, since the product of two integers is an integer here, therefore, we can say that A divides C here. Follow? So this is by the definition, because we have written here C is equal to the product of two integers, which is an integer, times A. So we can write A divides C. So we're done. So because we want to show A divides C. Now let's have here an example. Since 6 divides 18 and 18 divides 36, then we can say that 6 divides 36. So as simple as that. Now let's have here the following theorem that states that if an integer divides two other integers, then it divides any linear combination of these integers. So we have this theorem. If A, B, C, and M are integers, and C divides A and C divides B, then C divides the linear combination of these integers. So we have here the sum of MA and NB. So let me have an example for this before we prove this theorem. Okay, for example, let A be equal to 4, B equal to 8, and C equals 2. Now, in this case, for our assumption, we have C divides A. So we have 2 divides 4, and we have C divides B. So we have 2 divides 8. Now, in this case, by using the theorem, we can say that C, which is 2, divides M. A here is 4. So we can write here 4M. 4M plus NB. So B is 8. So we can write 8N or BN here. So that's it. Now in this case, we can, because C, M, and N are integers. So here, if M here is 2 and N here is 1, we have 4, this is 8 plus 8. So we have 2 divide 16. So in that case, we know that 2 divide 16. Why? Because we can write 16 as 2 times K, where K is 8. Now, let's prove this theorem here. Since C divides A and C divides B by our assumption here, so take note here that this is our assumption, ito, if, then this is our conclusion. We need to show this one. So from this, let's use the definition. So here there exists K1 here, K2 with this one. So A, you can write this as this one. A is equal to K1C. Then the second one, we have B is equal to K2C. Thus, we have this one. So take note here. By the way, let me write it here. So again, when we have C divides A, we mean A is equal to K1C for any integer K, for some integer K1. So existence lang man siya. And then if we have C divides B, we have this one. B is equal to K2 for some integer K2. Now, if we have here M, A plus NB, we have M, we have here A is K1C plus N, then B is here K2C. So that's why we have this one. So we factor out C. So we factor out daw nato ni si C here. So C times we have MK1 plus NK2. Okay. Next, we can say that C divides this one. So in this case, we can say, kay diba, we have written this one, kani siya, MA plus NB. We have written it as a factor, as the product of C and this one. Now notice that this is an integer. Why? Nga nang integer ni siya. Why is this an integer? Because M, K1, and K2, we have here the product of two integers is an integer. This is an integer also. And then the sum of two integers is also an integer. Therefore, the whole of this one is an integer. Now take note that by the definition, we can say nga kani daw si C divides this one. So we have M, A plus NB. Follow? Recall that if we have, just kuan lang. If we have here, say for example, this is D equals CK. So for example, this is D. This is our D. Then this is C and this is our K. Kani atong K. So from the definition, we can write C divides D, right? In the definition. That's why we have this one. And now, C here, this is our D, MA plus NB by using our definition. That's why we have this one. So we're done with our proof. We have shown that C divides this linear combination of the integers. For example, here, 2 divides 4 and 2 divides 6. So we can say that for M equals 2 and N equals 3, we have 2 divides 2 times 4 plus 3 times 6. So in this form, which implies that 2 divides 26. Then, for this case, for M equals 5 and N equals 7, we also have this one, which implies that 2 divides 62. Okay. So, let's have, by the way, this This theorem here is a generalization to any finite linear combination of the previous theorem. So in our previous theorem, we have here C divides A and C divides B. Now here, we have finite na siya. So up to A divides B sub n. So here, this is a finite linear combination. Whereas in our previous theorem, we have here only MA plus MB. Now, let me give an example. Let K1 be equal to 2 and K2 be equal to 1, K3 be equal to 4. So, this example for K1, K2, K3 lang siya. Finite. Anyway, finite man. You can have K4, K5, K6, and as long as finite. Now here, we can say that 3 divides 9, 3 divides 12, 3 divides 15. So, we know that already. So, this is our assumption, sa kaninang part. And then, by using this, we can say that 3 divides, so see 9, you have K1. So 9 or 2 times 9, we have K1 times 9 plus 1 times 12 here. K2 is 1 times 12 plus K3 is 4 times 15. Now we're using this one. And then we simplify. 3 divides here 18 plus 12 plus 60. And then that is equal to 3 divides 90. So, of course, 3 divides 90 because we can write 90 as, 90 equals 3 times 30, where 30 is our K. Now, let's proceed to the division algorithm. So the following theorem states somewhat an elementary but very useful result. So we have here the division algorithm theorem. If A and B are integers such that B is greater than 0, then there exists unique Q and R such that we can write A equals BQ plus R, where R here is greater than or equal to 0 but less than B. Now, let's have here an example. So, we let A be equal to 18 and B be equal to 7. So, from our division algorithm, we have A equals BQ plus R. So, we can have 18 plus 7. So we can have 18 equals 7Q plus R. So here, we are going to find Q and R. So unique na siya. The unique Q and R. So here, we can have Q be equal to 2 and R here is 4. So we can write this one as 18 equals 7, then times 2 equals 4, plus 4 rather. So here, 18 can be written as 7 times 2, which is equal to 14, then plus 4. So si Q na to is 2 and R is 4. Now notice here, R should be greater than or equal to 0, but less than B. So our 4 here, notice the C4 is greater than 0, pero less than siya ni 7, which is our B. Now here, Q is our quotient. Q is our quotient and R is our remainder. If we divide 18 by 7. Take note, if we divide 18 by 7, if you're going to use our long math division method, we have here 18, 7. So of course, this is 2, this is 14, and our remainder is 4. So this is our Q, and this is our R. So if we use the long division method. So this is our division algorithm. So A equals BQ plus R. So there exists a unique Q, which is our quotient, and R, which is our remainder, such that for our remainder, we have this condition. So of course, C4 should be less than 7. So let's have here a note. A is divisible by B if and only if the remainder in the division by algorithm is 0. So for example, if we have here, say 12, A is 12, and then B is 4. So of course, we can write 12 equals 4 times 3 plus 0. Here, Q is 3, our quotient is 3, and our remainder is 0. So that's it. Hence, we can say that 12 is divisible by 4. So in that case. Now, let's have here an example. If A is equal to 71 and B is equal to 6, so we have 71 is equal to 6 times 11 plus 5. So the 66 plus 5 is equal to 71. Here, Q is 11, and then R is 5. So take note how 5 is greater than or equal to 0, but less than 6. Another one, if A is equal to 50 and B is equal to 5, we can write 50 equals 5 times 10. So here, Q is 10, R is 0. So we can say that 50 is divisible by 5. So let's use the division algorithm to find the quotient and remainder when 76 is divided by 13. So we have here 76, A is 76 here, and B is 13. So 76 is equal to 13. What number plus this remainder? So here, Q is negative 8, and then R is 4. So we have our answer. Q is negative 8 and R is 4. Now in this example, can you use the katong long method, division? Division ng long method? Let's try here. Negative. We have here 13. So it's very difficult not to, when we use the division method here. So we cannot have here negative. But anyway, you can also use this one, pero medyo complicated siya if you use the long division method. So we know that this is negative 104. And then change the subtrahend. This becomes positive 4. So in that case, it's difficult to use the long division method for this case. So the better you use the division algorithm in this case. So this is our Q and this is our R. So medyo complicated if A is negative. So the better if you use the division algorithm. So we're done. We're done discussing the divisibility and the division algorithm. So God bless everyone.